We're going to look at the proofs from the quarter test review. I have actually already written up the solutions, but I'm basically going to describe the solution. So Mn is congruent to Ns, and Mp is congruent to Ps in the given. And then I was able to show that Pn is congruent to Pn. I'm going to prove these two big overlapping triangles, PMN and PSN congruent. Once those two triangles are congruent, I can prove these two outer triangles congruent. I did that by proving PQ congruent to PQ, and I did it by proving angle MPQ congruent to angle SPQ. And then I could get these two left side triangles congruent by side angle side, and that meant that angle MQP would be congruent to angle SQP because corresponding parts of congruent triangles are congruent. Okay, and I'll try to post this online as well, hopefully, so you can also see the written up version if you need to. This one was kind of long. I'm not necessarily sure that the solution I have here is the fastest one. There are a bunch of different possibilities, but I wanted something that would be pretty accessible here. So, okay, the big thing here is, of course, we've got perpendicular lines, so we have right angles, and of course, if angles are right angles, they're congruent. In addition to that, AB is going to be congruent to AC because of triangles isosceles, its legs are congruent. And the base angles of that big triangle are going to be congruent, ABD and ACD, because in a triangle, if two sides are congruent, the opposite angles are congruent. You can prove these two big triangles congruent then by the angle-angle-side rule, which I've done, okay? Then I came back and I showed, well, okay, if these two big triangles are congruent, then these two upper angles, BAE and CAE, are congruent. Basically, I decided to prove the two upper triangles congruent. And AE is congruent to itself by the reflexive property. And so the two top triangles are congruent by side angle side, which you can see down here. Once those two top triangles are congruent, you can say that BE is congruent to EC, and that's because corresponding parts of congruent triangles are congruent, and of course that means the triangle is isosceles. BEC is isosceles because it has at least two congruent sides. Are there other ways to do it? Sure. For example, when you get the two big triangles congruent, you could show that BD is congruent to DC, and that means that AD is a perpendicular bisector of BC. Point E lies on the perpendicular bisector, so that would make it equidistant from the endpoints of segment BC, and that would give you an isosceles triangle as well. So that's another option. All right, another proof here. This one here, they give you a perpendicular bisector. Remember that if you have a perpendicular bisector of a segment, any points that lie on that perpendicular bisector are equidistant from the endpoints of that segment. And you can just go down that perpendicular bisector and draw congruent segments. So that's the idea I used here. Since point E is on the perpendicular bisector, EB is congruent to EC. And since point A is on the perpendicular bisector, AB is going to be congruent to AC. You could use a reflexive property here. You could prove those two upper triangles congruent, which actually ends the proof because that's all they wanted you to show. All right. This one down here, a lot of ways to do this proof. They gave you WXY, that full angle there, congruent to ZYX, which is this angle over here. They told you that side WX was congruent to side WZ. I proved the two big overlapping triangles congruent, and I did that by proving XY congruent to itself. With the two big overlapping triangles congruent, that meant that angle W and angle Z were congruent corresponding angles. And then I had a pair of vertical angles that were congruent there and there. And is that, you know what, that didn't get into my proof. WRX, actually it did get into my proof. Let's see, vertical angles are congruent is what was supposed to happen in that step right there. Okay. Better written in an if-then form. But anyway, once we get these two triangles congruent, in this case by angle-angle side, you're going to be able to say that WR is congruent to RZ because those are corresponding parts of congruent triangles. All right, next set of proofs. This one's pretty quick. You're basically proving that if both pairs of opposite sides of a triangle are congruent, that it's a parallelogram. I decided not to use that fact, which would allow you to do this pretty quickly, but just to do kind of the basic version. So they told me that these two segments were congruent. They told me that these two segments were congruent. I proved the shared segment congruent using the reflexive property. You can see that right here. So the two triangles are congruent, and I want to prove AB parallel to CD. If you notice, I've got a pair of alternate interior angles here and here. And if I can prove these two triangles congruent, those two angles are going to be congruent. So I went ahead and said that ABD was congruent to CDB because corresponding parts of congruent triangles are congruent, and that was a pair of alternate interior angles that proved AB parallel to CD. So I kind of went the long way on that, but I think for that kind of proof, that's probably what was intended. 37, they tell you that these two lines are parallel. They also tell you that they're congruent to each other. I drew in segment TW. You can do that because 2 points determine a segment. And because of the parallel lines, these alternate interior angles are congruent. That's angle ETW and XWT. I proved TW congruent to itself using the reflexive property. So these two triangles ended up being congruent by side angle side. And I wanted to show that the other lines were parallel, these two. So if I could get this pair of alternate interior angles congruent, we were good to go. And those are corresponding parts of those congruent triangles. So XTW congruent to EWT proves that TX is parallel to EW. And our last two proofs. This one I think was on the test, at least in 2022. You have a rhombus, so of course all sides are congruent. We've got some perpendiculars here. I went ahead and showed that that was a right angle and that was a right angle, and that they were congruent because perpendicular lines that intersected a right angle. I said that segment MG was congruent to JG because all sides of a rhombus are congruent. So if a quadrilateral is a rhombus, then its sides are congruent. And then I showed angle G was congruent to itself. I was basically able to show these overlapping triangles congruent by the angle-angle side rule. And once I did that, MH and JO were corresponding sides of those two triangles. All right, the last one, this was on the quiz, at least in 2022. These two outer segments were congruent to each other. And that means that these two base angles are going to be congruent because the big triangle was isosceles. So I actually put that in before the given. So if I have two congruent sides in a triangle, if two sides are congruent, then the angles opposite the sides are also congruent. They also told me that CBD, this angle here, is congruent to EFD, which is that angle there. And I was trying to prove that BDC, which is this angle right here, is congruent to FDE, which is that angle on the other side. I've got two pairs of triangles. They're not necessarily congruent, but they already have two pairs of congruent angles, and the no-choice theorem is going to enable you to show that last two pairs of angles congruent. So that would basically be if two pairs of angles of two triangles are congruent, then the third pair of angles is also congruent. And that's all you need to do.